Okay, so we're going to continue with our section on titrations, this time looking at weak acid, strong base titrations. Last time we looked at strong acid, strong base. Well, the difference here is that weak acids don't completely dissociate. So we have to deal with that weak acid dissociation equilibrium before we can move on with the titration. So this is very similar to buffer problems that we talked about in section 3. The weak acid will react essentially to completion with the OH minus because it's coming from a strong base. And so first we do the stoichiometry problem because we need to get the information for what the concentrations are after the reaction. And then we do the equilibrium problem to determine the position of the weak acid equilibrium and find the pH. So we're breaking it into 2 parts, like we said, very similar to a buffer problem. So let's start with 50 milliliters of a 0.1 molar acetic acid. Acetic acid is a weak acid. And we're going to titrate with 0.1 molar of NaOH. So first, just like we did with the strong acid, strong base, we want to look at what's the case before we add any NaOH. This is a very typical weak acid calculation, so anything from chapter 14, and we would get a pH of 2.87. So you could go through and do your ICE table, take your 50 milliliters of your, 0.1 molar acetic acid, and calculate your pH. Okay, but we're not going to go over that in the interest of time. So now that we've got that, let's start adding our NaOH. Well, before the reaction, we have our weak acid. It's not dissociating completely because it's weak. Our strong base will dissociate completely, so we have the OH minus, the Na plus, and the water. And let's do the stoichiometry problem first. So we're starting with this reaction. We know we have 50 milliliters of, 0.1 molar? Acetic acid. And so we multiply that together to get the number of moles. This is going to give us 5 millimoles to start with. Excuse me. We know we have 10 milliliters of 0.1 molar NaOH, and so when we multiply those together, we're going to get 1 millimole. And we have no acetate ion, and we're not counting water. So this is before the reaction. Now for after the reaction, we know that the OH is going to react, so we're going to subtract 1, add 1 here. And so for our after reaction, we should have 4 millimoles of acetic acid, no millimoles of the hydronium ion, or hydroxide ion, and 1 millimole of our acetate ion. Okay. So now we can take that information and go to the equilibrium problem. Well, after the reaction, we still have some acid left. We have our acetate ion, the sodium ion, and the water. Remember, the OH was completely reacted. Since acetic acid is stronger than water, and we could determine that by looking at the Ka values, and we have some acetate ion already present, that's the reaction that we're going to go with. And so if we do our ICE table, we know that we had 4 millimoles of acetic acid left, but if we want to get the concentration, we need to take into account the entire volume. Well, we added 10 milliliters of our sodium hydroxide, and we had 50 milliliters of the acid, so this is 60, and that will give us 0.01667 molar of our acetic acid. If we look at our H+, we initially had 0, and we had 1 millimole of our acetate ion, but we also need to divide this by 60. Oh, I see I made a mistake. Let's see here. Whoops. There we go. Okay, so this should be 0.0667, and this one is our 0.01667 molar. Okay, so our change, we're going to subtract x minus x. Oh, dang it. Plus x, because there's my arrow. Okay, and then we end up with 0.0667 minus x, and 0.01667 plus x. We can put this into our Ka. We know Ka is equal to H+, our acetate ion, over our acid. And we can also make our approximations. And we know our Ka value is 1.8 times 10 to the negative 5th. And that's why it's a stronger acid than the water, because water is smaller than this. Okay, so now we can plug in, so we get x. We have our 0.01667 plus x, but remember we're just going to approximate that to 0.01667. We're going to say that x is very small. And we're going to do the same thing with the bottom one. And so if we solve for x, this is a parenthesis, we should get that x equals 7.2 times 10 to the negative fifth. So you could obviously pause and double check this. This fits right into our approximations as within 5%, so this is an appropriate value for x. That means this is also equal to the H plus concentration, and so we can take the negative log of that, giving us a pH of 4.14. Okay, so very similar to a buffer problem, stoichiometry, and then your equilibrium. Okay, so we added 10 milliliters, now let's add 25 milliliters. So it's very similar to the previous situation. We need to do our stoichiometry problem first. So we have our acid. We know we had the 50 milliliters and the 0.1 molar, so we're going to start with 5 millimoles just like before. Now we have 25 milliliters of a 0.1 molar, so this gives us 2.5 millimoles. And we know that we're starting with 0 of this, and we're not counting that. So now we're going to subtract 2.5. We're going to add 2.5 over here. So here the difference between this and the strong acid is, with the weak acid we have this acetate ion. With the strong acid, that wasn't the case. So for after reaction, we should have 2.5 millimoles of our acetic acid, 0 millimoles of our water, and 2.5 millimoles of our acetate ion. So now let's move on to the equilibrium part of this. Major species after reaction, very similar to the previous one. Here's our reaction, so we have our ICE. This time we had 2.5 millimoles. Now our volume has changed because we had 50 milliliters of acid, but 25 milliliters of base, so that's over 75. And so that is going to give us 0.033 molar. We don't have any H plus to start with, and our acetate, we also had 2.5 millimoles over the same volume, and so we also have 0.033 molar. Our change, we're going to subtract x plus x plus x. So our equilibrium is 0.033 minus x, and 0.033 plus x. So again, we can plug into our Ka, which was what, 1.8 times 10 to the negative fifth. We're going to make the same approximations we did before, so here's our H+. We're going to assume X is very small, so our acetate ion becomes just 0.033 molar, and our acetic acid becomes 0.033 molar as well. As you can see, our concentrations are the same for the acid and the acetate ion, and so it ends up that X is just equal to Ka, which is also equal to the H+ concentration. So H+ is equal to 1.8 times 10 to the negative fifth. And that gives us a pH of 4.74. Okay, so hopefully what you noticed is that the concentrations of our acid and our acetate ion were the same. We would call this halfway to the equivalence point. So half of the original acetic acid was converted to the acetate ion. Okay, so we started with 5 millimoles and 2.5 of it was converted, meaning that they were the same concentration. And so because of this, we can neglect the effect of dissociation, meaning that the equilibrium is equal to the initial concentration. And so that gives us that Ka is equal to H+, just like we saw in the problem. And so because H+ is equal to Ka, that means the pH is equal to the pKa. So if you notice that you're halfway to the equivalence point, you can just go right to this. You could go through the whole problem like we did, but because it's halfway, this will be true. Okay, so now let's add 40 milliliters of NaOH. Very similar to the two problems we did with the 10 and the 25 milliliters. And so you can go through and do this, but you should get a pH of 5.35. So now let's move on to 50 milliliters. Okay, well, we have now reached the equivalence point because all the OH minus is going to react with all the H+, because we also had this quantity for our acetic acid. So here our major species are going to be the Na+, the C2H3O2-, and the H2O, because all the OH from the base has reacted with all the H+ from the acid. So we know that bases want to accept protons, and this is our weak base. And the only protons left are going to be from the water. So we end up with this reaction. So we have our weak base plus water producing our acid and some OH- ions. And so this becomes a weak base reaction if you think back to like when we did the salts. And so we need the Kb value, and so we get that by taking our Kw over the Ka for that acid, and this gives us the Kb for our C2H3O2 minus. Okay, so now if we take a look at this, we can do our ICE. And so we know that we have 5 millimoles of our acetate, but this time we have 50 milliliters of the acetate and 50 milliliters of the base, and so that gives us 100 milliliters. And so that gives us 0.05 molar. Remember, water we're not going to include at all, and we're starting with 0 of both of these. And so then we have a minus x plus x plus x, and so we have 0.05 minus x, x, and x. Well, remember, this is a weak base, so we're going to do our Kb. That gives us our acid times our OH minus, divided by our acetate. But we're going to make our approximation, so we're just going to make it 0.05. And that Kb value was, I forget, 5.6 times 10 to the negative 10. And so we end up with x squared over 0.05. And so we can solve for x, and that's approximately equal to 5.3 times 10 to the negative 6. So we can check our approximation, and it's completely okay. This x is equal to the OH minus concentration. So if we want to find pH, we have to do a few more steps. So we know that H plus times OH minus is equal to Kw. And so we can take Kw over our OH minus to give us our H plus. And so 1 times 10 to the negative 14 over our 5.3 times 10 to the negative 6. And that gives us a value of our H plus of 1.9 times 10 to the negative 9. So now we can take the negative log of that to get our pH, and pH is now equal to 8.72. And so this is the equivalence point. So if you remember the equivalence point for strong acid, strong base, the pH was 7. Here it's not. And so the pH at the equivalence point of a titration of a weak acid and a strong base is always going to be greater than 7. And that's because we have these anions, the OH minus, remaining in solution, and it's a base. So now let's go past the equivalence point and go to 60 milliliters. So now we have excess OH minus, and so we're going to do the stoichiometric part first. So same thing. So before reaction, I believe we were starting with 5 millimoles because we had the 50 milliliters and the 0.1 molar. Now for the OH, we have 60 milliliters and 0.1 molar, and so that gives us 6 millimoles. None of this, 0, or well, I guess we're not even counting the water. So we're going to subtract 5 because it's 1 to 1. We're going to add 5 here. So after reaction, we get no acetic acid. So remember, just like we did with the strong acid, strong base titration, now we're reacting the acid completely. We're being left with OH minus. We have 1 millimole of OH minus left and 5 millimoles of the C2H3O2 minus ion. So the major species after the reaction, no acid. We have the Na plus from the base, the C2H3O2 minus, the OH minus, and the water. So we've got two bases. We have this as our weak base, and we have the OH minus. Well, the OH minus is stronger, so it's going to be dominant. And so just like before, we can find the concentration of the OH by taking the millimoles of OH that are in excess divided by the total volume. So we have 1 millimole of OH left. Our total volume is 50 from the acid plus 60 from the base, so 110. And that gives us 9.1 times 10 to the negative 3 molarity. And so this is our OH minus. So if we want to find the H plus concentration, we have to take Kw divided by OH minus. So we do that. That gives us a concentration of 1.1 times 10 to the negative 12. And then we can take the negative log of that to get our pH of 11.96. Okay, what if we added 75 milliliters of base? Very similar to what we just did. Okay, so you could go through all of that, but you should get a pH of 12.30. Okay, so let's look at pH curves of a weak acid and a strong base. They're going to be different than the strong acid before the equivalence point, but not after the equivalence point, because the OH minus is controlling the pH at that point. So we have no weak acid or strong acid left. And as you can see, the weak acid levels off at halfway to the equivalence point. And this is because optimal buffering is going to occur when the concentration of the acid is equal to the concentration of the conjugate base. Remember, we looked at that calculation, and that's happening about right here. And the equivalence point for the weak acid is going to be greater than 7, so we're looking for something, maybe about here. It's definitely greater than 7. But if we look at the equivalence point for our strong acid, I'm going to guess about here, and that's lining up almost exactly with 7. The amount of acid, not its strength, is what's going to determine the equivalence point. And so the pH at the equivalence point does depend on acid strength. Okay, so the pH depends on acid strength, but the amount of acid is going to determine where that equivalence point occurs. So the reason for this is because the weak acid is going to have a stronger conjugate base. And so that's where that's coming from. So if we take a look at all these Ka values, as the Ka value gets larger, you can see, that we've got this more leveling off and then this larger range, for our equivalence point versus Ka of 10. You're almost seeing no change whatsoever. So the shape of the pH curve is going to be affected by acid strength. Okay, so what we're going to move on to next is how to calculate Ka.